Hello, students. What I'd like to do is just to review some of the problems dealing with first-order reactants. First, the method of initial rates. You can see the problem as well as my work here. You really have to know what to do with what information you're given. If we look here, here's our reaction, and you're asked to obtain the rate law, and right away we see that you're given 3 different experiments where you varied the amount of each reactant and measured the initial rate. So the rate of the reaction right off the bat. So we can use this to really analyze how the change in each reactant had an impact on rate. So what we want to do is look between the different experiments and isolate where only one of the reactant amount was changed, the other one was kept constant. If we look from experiment 2 to experiment 1, we tripled the amount of the ClO2 while the hydroxide amount was kept constant. When that amount was tripled, the rate increased 9-fold, which means the order of ClO2 is second order. For the hydroxide, if we look from experiment 2 to experiment 3, we did not change the amount of ClO2. We tripled the amount of hydroxide, and the rate tripled. So that order is 1. Whenever you are satisfied with the rate law, then you can choose one of your experiments, input the concentration applied to the different orders that you determined with the rate to find your K value. Please be very, very careful about the units, and you can see how we calculated the K here. This next example, if you want to pause and take a look, I hope you can see which experiments I utilized, how I came up with this individual rate law, the value for K, and then once we know what the rate law is and have determined the rate constant value, we can then substitute in the value for the concentrations in experiment 6 with our K to actually determine rate, and that's what I did in C, which is shown there. So if you want to pause and take a look at that, please do so. This third example is a little more complicated than we'll see. We have something to the second order, first order, and half order. We won't see that with the method of initial rates. If you want to pause and to look at my work, which I've continued to show at the bottom here, that will reveal to you how I determined what the order was on your hydrogen ion. However, these following reactions are dealing with looking at the half-life situation. Whenever you are asked, I'll wait till this comes up, in the fourth problem for an amount after a certain amount of time, that's when we want to lean upon the integrated rate law. So as soon as you are, again, incorporating any kind of variable of time, we want to lean upon this equation here. Now you're given the initial concentration and the concentration of your reactant after a certain amount of time. The reason why you're given that is because we need to find K. Because ultimately, you're asked for the concentration of A after 256 seconds. However, we're limited if we know our time, initial concentration of A, we cannot find A at 256 seconds unless we know the value of K. So we need to find that first with that first given amount of information and then plug that in to find what the concentration would be later. Again, please pause this if you want to take a deeper look at my work. Beginning with number 5, that's when we are going to be incorporating half-life. I very, very strongly encourage you to use this form of the integrated rate law because we're going to find wording such as we see in number 5. How long will it take for 25% of the remainder of the reactant to be left, or 75% of the reaction to be complete. So please take a look at my work. The first thing I did was found half-life as you were asked in A. Remember, with the first order reactant, half-life is constant. It is simply 0.693, or natural log of 2, divided by K. We're told what K is, so we just input that to find our half-life. Then, coming up with some kind of a ratio, 25% of what it was could be 1 over 4, 1 over 0.25, or 100 over 25, and so on. And so what you end up getting, natural log of 4 over K, to find the time it would take for 2 half-lives. And you could mentally reason that out, but of course we want to support that with mathematics. Number 6 isn't quite as clear-cut because you're actually asked how long will it take for 90% of the reaction to be run. And so here we're looking at a ratio. If we want to do A naught over A, 90% of the reaction to be done would be a ratio of 1 of 0.10, 100 to 10, or what would be 10. And so plugging that in, we find that the time, because it asks you in hours. So because your K is given per second, you'll get seconds out, but the problem is asking for how many hours, and your final answer is 330 hours. Please feel free to rewind if you need to go back and look at anything in detail, and of course you can always ask me in class if further interpretation is needed.